All right. Good evening, everyone. Please let me know if you can hear me fine. Just let me check the microphone. Yeah. I hope you can hear me fine. Yeah. Please let me know. You can just unmute yourself and let me know, or you can write in the chat box also. Okay. All right. So we have 13 participants, actually 14 right now. And let me welcome you again on our third session on Calculus Connects. And I'm really positive that this session is also going to be helpful and meaningful for all of us. And we are going to learn something interesting. Okay, so can you please confirm me if you can hear me fine? Yeah, so I can just simply move on. Yes, anyone? Perfect. Thank you, Manur, for your response. All right, so let's continue. And actually, I got some feedback or some queries from some of you. I will try to also address those questions during our session. But let me also remind you, if you have any question or concern or feedback, please do let me know. You can send me an email directly, or you can also fill out the form. Okay. All right. So so this is our third session on Calculus Connects, and the agenda for this session is a quick recap. I mean, we will discuss what we have done so far very quickly. Then today we are going to focus mainly on derivative. We are going to approach them from graphical point of view, from the theoretical point of view, and we will also see some applications. We will see what do we mean by optimization and how we can use the very idea of derivative to solve like differential to solve many problems, especially the equations which is changing, and find the maximum or minimum value. And at the end, we will also going to have a quick introduction to the antiderivative, which is also called integration sometimes. We will discuss them in details. We will also see the difference between antiderivative and integrals. Most of us actually, we feel or we think that they are the same thing, but there's actually a minute difference. We will also discuss them. And in the next two sessions, next session is going to be based on mainly on integrations, and the last one will be more on the application. So we will see, we will use actually GeoGebra and some other apps in detail, and we will try to understand them further. Okay, so let's try to be connected with calculus. Yeah, let me move on. So actually, before we start the topic derivative, I just want to discuss, I got this question earlier. You know, people were asking, for example, like, you know, why, let's say the infinity minus infinity, why it doesn't give you, why it's not equals to zero, something, you know, like, why don't we simply say that this is zero, or maybe infinity over infinity, right? Why it's not equals to one? Because, you know, these are the same number. So why don't we simply, you know, cancel them? For example, if you have 7 over 7, that is equals to 1. But why not infinity over infinity, or infinity minus infinity? Okay, so I got this question, you know, even though we discussed, but I thought that it might be a good idea to start with this concept. So before I discuss this further, maybe any one of you want to say something about why infinity or infinity, for example, like this guy, why this is not equals to 1? Maybe can you just say in a quick sentence? Yes, anyone, or if you want to give any input, so let me know very quickly. Okay, I got one response from Bilal. It's a concept. Okay, actually that's the thing. Actually, it's a concept, but I will discuss. I mean, that's not that much simple. That's actually what many people actually. The size of infinity is unknown. Yeah, that's also a very interesting idea. I love. So, and Bilal is saying infinity is not a number, so it's a concept. Okay, actually, there's a thing. Actually, infinity is a concept. But let me also emphasize here. Even, you know, for example, like numbers 2, 3, or 4, or 7, these are also concept. So, for example, this might not be very much clear. The thing is that, you know, when I say 3, you know, 3 itself, it does not exist. You know, if I ask you what is 3, there is no such thing as 3, right? maybe, of course, you can tell me 3 apples, 3 fingers, 3 eggs, or whatever. So 3, but the 3 itself is also a concept. It's just inside our mind. There's no such thing as, there's no as such physical thing as 3 itself. So actually, essentially, like generally all the numbers are conceptual numbers. They're all concept. For example, 2 is also a concept. 2 plus 2 equals 4. Like itself, like this is also a concept. But when we apply them, for example, when we say we have 2 eggs and when we add 2 more eggs, of course we get 4 eggs. But 2 itself is also a concept. So infinity is also a concept. That's very true. But the thing is that it's not actually like a fixed. When we say 2, we mean something like everyone agrees on. When we say 2, everyone agrees on some common definition. But in the case of infinity, the definition, like, because I think Ela was saying the size of the infinity is unknown. So since we don't know exactly the size of infinity, that's why it's a bit different type of concept. That's why actually, like when people say infinity is not a number, it's a concept, they mean actually that thing, that they're unable to quantify or merge like the concept to particular number. I mean, that is the reason, like 1 over infinity, it does not signify any number. For example, like sometimes we say, okay, 1 over infinity equals 0, for example, like this guy. We generally say this thing, but that's actually not very true. We should say actually 1 over infinity approaches to 0, like approximately equals to 0 in a limiting value. And once you understand this idea, since infinity is a concept, but everything is a concept actually. In mathematics, everything is a concept. There's no such thing as concrete. It's just the concept. But the problem with infinity is that it's not sizable. We don't know the size. We don't know the magnitude of infinity. That's why when we say infinity minus infinity, it may not be equals to 0. I mean, it can be 0, but it doesn't have to be. Sometimes, like to see actually, like why is that so? Let me just give you a very quick example. For example, if I say, how many numbers do we have between 1 and 2? So there are infinitely many numbers, right? I mean, 1.1, 1.11, and 1.112. If you also include the decimals, so actually there are infinitely many numbers between 1 and 2. Similarly, there are also infinitely many numbers between 1 and 3, right? And as you can see, the infinity between 1 and 2 is smaller than the infinity which is between 1 and 3. So actually, there's still a debate, and when it's about infinity, things change very drastically. And I mean, maybe we can discuss them later on at some other point, but that was the idea. So we say infinity is not a number. We mean it's a concept, but we also mean that it is the size of the infinity is not specific. That's the very reason we cannot do the normal operation with infinity. All right, so let me move on. This was actually the thing it was discussed, so I thought to discuss this again. Let's move on to our main topic here for today. As I told you, our main focus is derivative. And so we will try to define the derivative of different basic functions and power rules and chain rules and product and quotient rules also. So we will discuss those things. Maybe I might be quick in defining and explaining those rules, but since we have limited time, so I hope you will follow along. And of course, you can easily find the details information in the textbook, but our goal is to understand them maybe from the conceptually. Okay, so let's continue. First thing first, let's discuss, maybe for some of you it might be a new thing, so like a symbology, or like the symbols we use to define the derivative. So basically the derivative, we use dy over dx. This we used earlier. Sometimes we also use dot on top of f dot. And yeah, actually, it was the Leibniz and Newton. They were the one who invented officially in the calculus, and they were using different symbols. So that's why we use different symbols for this very concept. But sometimes, it might be easy to use the dot thing, for example, because, if you want to find the second derivative, if you want to find the derivative 2 times or 3 times, it might be much easier to simply put 3 dots on top of it. Yeah. So the 3 dots mean the third derivative. So you differentiate 3 times. So this is another way they're the same thing, by the way. They mean the same thing. Similarly, we can also use this thing is called prime. So f prime of x. So that's also a way to represent derivative. Okay. So dy over dx, this is called f dot, this is called f prime of x. So these are all first derivative. And for the second derivative, you might see this thing. So let me also write here. So d2, we call them, or we read them as d2y over dx2. Okay, so this is how we pronounce them. That means the second derivative. And this equals f double dot. Okay, so double dot simply means that it's a second derivative and the f double prime of x. Okay, or sometimes even you can use y double dot. It's the same thing, you know, f of x or y of x. And we can continue representing these things for the third derivative and the fourth derivative also. Okay, so don't be confused when you see different symbols. They mean the same thing. All right. Okay, so first thing first, you know, in the earlier session, we discussed very quickly at the end of the session how to define a derivative from the graph. So today, actually, we will focus maybe half an hour on that particular thing, because that's very important to understand what derivative means and what it signifies. So a quick recap. We discussed, you know, when for a graph of f, if it is increasing, then the graph of the derivative, you know, you see f prime here. So the graph of the derivative, it is positive. So remember, this is very important. If the function is increasing, the derivative is positive. So if you make the sketch, it should be in the positive, on the positive side. So for example, if you have this number plane, so the positive mean it should be in this quadrant, or this quadrant, yeah, because this thing is positive. So it has to be in this area, in this region. Okay, when the graph is decreasing, so the derivative is going to be negative. It's going to be below x-axis. So remember this thing. It has to be below the x-axis. That means it's negative. And actually, that's also very important thing. When it is maximum or minimum, or you know, it's called the turning point. Also, it has many different names. We will discuss them. This is also an interesting thing to understand. So whenever the graph is at the minimum or maximum point, the graph of the derivative, or f prime, is 0. So these three things are super important, and if we understand these things, we can simply quickly sketch the graph of many different functions. Okay, so please note it down, because we are going to use this idea in our upcoming slides, and we will try to find the derivative of different functions. And this way you will also maybe refresh your understanding of the fundamental basic functions. If you remember, in the previous session, we discussed some basic functions: exponential, logarithmic, sine, cosine, and polynomials. So we will try to find the derivative maybe in details. And then we will also find the derivative from the first principle, or from the theoretical point of view, from algebra, because that's also important. Okay, once you know this idea, let's move on. I have this thing actually, and maybe, you know what, I'm going to sketch the derivative of these functions, but at the same time, I also want you, you know, just don't look at the screen. Of course, you should have a piece of pen and piece of paper with you and pen. So I also want you to quickly sketch the derivative on your paper right now, and I will also do it, and then you can also cross-check. Okay, because I mean, the practice is important. You know, they say the ultimate way to understand math is to do math. So I think it's time for you also to do some activity. So please take out your pen and paper and start sketching something there. So yeah, I'm also doing it here on the screen. So let's do it together. So by the way, these functions, they're all, we can categorize all these functions as, can someone tell me the name of this function? You know, there are 6 different functions, graph. What do we call them all together? Hasan is saying it's polynomial. So is that so? Yeah, it's polynomial. And you know, the first function is the degree 0. That means it's a constant function. And the second function is linear, then quadratic, and then cubic, and quartic, and quintic with degree 5. So these are all polynomials. And I told you earlier, the polynomial functions, yes, thank you, Shayan and Hasan. The polynomial functions, they have the property that the functions are smooth. They are very, very well behaved function. As you can see here, even though you have lots of, you know, turning points, maybe in this case, for example, but the functions are very smooth, you know, they're very, what do you call them, you know, Yeah, they are turning also very smoothly. There's no sharp turn, so they're not misbehaving. Okay, and that's why the polynomials are important. And I also told you they are used also in the algorithm of different programming, and also all the functions. Actually, you use your calculator to find the value. They use polynomials to approximate the values of those functions. So, for example, if you want to find ln 69 on your calculator, so what actually the calculator is doing, actually it is approximating that function into polynomials, and then it finds the value, because the calculator or the computers, they can only add different terms, right? Because it's a binary system. So polynomials are important. It is used to define all the functions, actually, approximately all the functions. Yeah, so let's try to find the derivative of these things. The first thing first, it's a constant function. So when it is constant, and we know the derivative mean how something is changing, right? So the first function, if it is a constant, so it is not changing. So the derivative must be. So can someone tell me what should be the derivative of this function, or where should I plot the graph of this function? I'm also hoping that you're also plotting on your notebook. Yeah, so it has to be 0 because there is no change. Yeah, thank you, Elaf and Wakas, Tariq. So the derivative, I'm just sketching with the red color. So the derivative is going to be 0. And the second, linear function, so it's not constant, it is increasing, but it is increasing with a constant rate. So the derivative must be a positive value. Some derivative must be constant, perfect, yeah. So, but it's not 0, it's something. So let's say, we're not interested in the exact value, but we just want to understand. So let's say it is somewhere here, okay. So this means the derivative is constant, but non-zero. So it is changing, the graph is changing, but it is changing with a constant rate. Okay, then we have a quadratic function, and which has a degree 2, right? So this actually is an interesting function, because in the beginning, the function is decreasing, and then it start increasing. Okay, so as you can see here, in this region, the function decreases, yeah? It goes down, and then after some time it starts increasing. Just a second. Yeah, sorry. All right. So in order to sketch the graph of this function, let me erase this thing first. So in the beginning, we know when the function is decreasing, the graph must be negative, and when it is increasing, the graph should be positive. So it's going to be, that means, in this region, and by the way, the first thing first, at this point, we also know at the turning point, or the minimum or maximum point, the function becomes, the derivative becomes 0. So when the function at this point, the derivative must pass through this point, origin, because that at this point the graph, the derivative should be 0. And then, in the beginning, before this point, the function is decreasing. That means it has to be negative. Let's say something like this. And after this point, the function is positive. So it has to be like this. So this is the derivative. Okay. That means, as you can see here, the graph, the derivative of a quadratic function is a straight line. Let's keep that in mind, because we are going to find like a rule to generalize this idea. Okay, then we have actually a cubic function. Cubic function, and this looks something like this. So in the beginning, it is increasing. Then at some point, it becomes, it has a turning point. Then it starts decreasing in this interval. Then at this point, the derivative becomes 0. Then it starts increasing. So what I will do always, whenever you have this kind of thing, you will always start with with these points, the maximum or minimum point. That means, since there was the maximum point here, so the graph must be 0 at this point. And similarly, the graph is the derivative must be 0 at also this point, and so on. So let's see what happens before this point. This is because we know for sure the derivative must be the derivative must be 0 at the maximum point. So before this point, since the function is increasing, so the graph of the derivative must be positive, like this. Yeah, so see, it is positive. And after this point, since the graph is decreasing, as you can see, the graph must be in the negative region, and it has to go back up at this point, and it will continue because after this point the graph is again positive. So now we have the graph of the derivative function. Let me know actually if you need more clarification. In the beginning it might be confusing, but I really urge you to understand this very idea. So we use three simple rules that at the maximum or minimum point the derivative graph is 0, and if it is increasing it has to be positive, otherwise it is negative. And actually the Khwarizmi is also suggesting, it writes to a degree lower every time. So whenever actually, as you might have noticed until now, the derivative graph is always 1 degree lower. So if the function is cubic function, the derivative is quadratic. Okay, but let's see if that is the case for the quartic and quintic functions, the next two. Okay, let's see if that is the case, and let's try to sketch the derivative together. I'm hoping that you are also working on your notebook. So let's see. So first thing first, I'm going to start from this point. I will find the minimum or maximum point. So this is the minimum point, this is the maximum point, and this is the minimum point. And I know at these points the derivative function must pass through the x-axis. So I will simply label these 3 points here, here, and here. Okay, and then it's quite simple. Before this point, the first point, before this point, since the graph is decreasing, as you can see, it is going down, so it has to be negative, like this. And after this point, actually, since the graph is increasing, it has to be something like this. Actually, I'm not very much focusing on the magnitude. I'm just sketching the very idea. Okay, then it will go down again, and it will move up like this. So it's going to be, the shape would be something like this, plus minus. So actually it is right, as Khwarizmi suggested, whenever we find the derivative, it is always 1 degree less than the function itself. Last thing, I'm doing it very quickly, here and here and here and here, the function is going to pass through these 4 points. So before the first point, the function is increasing, it has to be positive, then it becomes 0, and then like this, and then like this. So as you can see here, since the function was quintic function with degree 5, the derivative is a quartic function, okay, with degree 4. Clear? So I'm going to also generalize this. We will also learn about a formula, which is called the power rule. But keep that in mind. First of all, we have to understand what is happening and so on. Let me move on to the next slide. Derivative of a sine function. That's also very interesting. I mean, some of you might know, maybe if you have done already some calculus, or if there are some teachers, the derivative of sine, you already know the answer, but we will try to find out, we will try to derive them. Okay, there's also a way to derive them, from the first principle or from algebra. Maybe we will see if you want, so we can also do that. But first, let's try to find the derivative of sine from the graph. And why we do so, actually, we also have to reflect what is happening, because sine function is also very important. We will see also some conceptual background of the sine function. So remember, always the sine function starts from the 0. It's a very, very nice curve starting from 0. It's like a wave like this. Yeah, maybe cos, you might not like cos curve. Cos, it starts from the maximum point. So remember that thing. This is very important. And yeah, it's also like a wave, of course, if you continue. But sine is more like a noble kind of function. It starts from 0 and very, very nicely curved. Okay. One thing more I also want you to appreciate about sine curve, that the maximum value of sine curve is 1 and the minimum value of sine curve is -1. So maybe we can discuss at some other point. We can also represent a sine function with a percentage. The percentage also starts, like the percentage mean like it starts from 0 and the maximum value of a percentage is 1. Also the probability, the minimum value is 0 and the maximum value is 1. Of course, the minimum value of sine is -1. But if you talk about the magnitude, it also gives you the same thing. The magnitude of sine x is from 0 to 1. So that means the sine, we can also use it for the probability and for the percentages. But maybe we can discuss them later on in detail. Like generally, I would also invite you, when you study any mathematical function, just remember that they're always connected. There's always a connection between everything. Actually, you always find a connection if you look properly. It's not actually easy, of course. It's very difficult. Scientists, they spend hours, maybe years, months to find a unification. But this is actually like a universal truth, I can say, if you allow me, that everything is connected, especially in mathematics. So, for example, like sine is about curve, but it has also some connection with probability and also the percentages and so on. And later you will see when we define the particles, their probability functions and wave functions, sine also be used there and all those things. Perfect. So let's try to find a derivative. Yeah. So derivative means the sine function. The thing is that it is changing. It was in the beginning it was 0. Then it took the maximum value and minimum value here. Then it comes up. So it was changing. It means it must have a derivative. And the derivative is also not a 0 or constant. The derivative is also changing because even though one thing more you have to also understand. Let's say the interval, this 30 degree interval, right? The first interval, the change here is much more than the change in the last 30. Right? If you go from 60 to 90, as you can see here, the change is very tiny. You see, this is the change. But in this case, when you go from 0 to 230, the change is this much. That means when the function is changing, the change is also increasing. The change is also changing, by the way. Okay. Not increasing, so the derivative must be decreasing at some point. So just keep that thing in mind. So the sine function, it also represents something which is changing, but the change becomes slower as you go away from the 0 degrees. Yeah, if you go until 90 degree, the change becomes slower. The rate of change becomes slower and lower. Okay, so let's discuss the derivative now. So in the beginning, the function was here. Sorry. In here, and the function is increasing. That means until this point. So okay, first again, let's try to sketch the maximum and minimum points, because at those points the derivative must be 0. So since the maximum point is here, so the derivative function must pass through this point. Then we have second maximum. Actually, in this case, it is minimum value here. That means the derivative of this graph must pass through this point here. First, okay, so then before this point, what is happening? Yeah, so before this point, since the graph was increasing, you see, so the derivative must be positive. So actually, if you allow me, I can simply sketch the graph like this. Okay, and if you recall, this curve actually, it resembles like a cosine x. Okay, so that means the derivative of sine x. So if I write here sine x, and if I put this symbol, the prime, this also means the derivative. This equals cos x. Okay. All right, but actually, when I say okay, you should be a bit reluctant. I mean, even though this looks like a cos x, but how can we be so sure that it is a cos x? For example, like I can also sketch another graph like this. Like this, use different color. It can also be like this, like a V-shaped graph. Just a second. Someone has a question for just give me a second. Okay, so first of all, the graph can also be like a V-shaped curve. So why do we know it? How come we know it's going to be a cos x? So even you should not be accepting this as like okay, so the graph of sine, the derivative of sine x is cos x. So there are also some more ways to ensure that the graph of sine is cosine. Okay, we will discuss maybe when we study the theory of derivative and from the first principle. Okay, Khwarizmi, you can unmute yourself. I think you have a question, so please go ahead.
Hi, hello. Can you hear me?
Yeah.
Okay, all right. So the question that I wanted to ask was that until 90 degrees, it is increasing, right? But the function that we draw, are you saying that it's in the positive quadrant, which is why we're saying that it's in the positive side? Like, if it's increasing, then why is the direction downwards?
Okay. So
So similarly, right? So after 90 degrees, it increases, but then it goes to the negative quadrant.
No, after 90 degree, as you can see here, the function is decreasing. How do you know? Like, why you say
Right.
it is increasing?
So yeah. So in the sense of like a derivative function, right? I understand that why we've drawn it downwards is because at 90 degrees, it's at the maximum point, and hence the derivative would be 0, right? Which is why the direction of the derivative function is downwards from 0 to 90. If like that's how I'm making sense it to myself, right? So but after 90, the value then starts increasing until the maximum, which is at 180, right? So for the derivative, the value should be maximum when the function itself is 0, right?
Okay, not actually. You know, I make this curve from 90 to 270. Yeah, just have a look. From 90 to 270 degrees. If you tell me if is the function increasing or decreasing from 90 to 270. So this red curve.
It's decreasing.
It's decreasing. That means during this interval, the derivative has to be negative. It must be below x-axis.
Right.
Okay.
Right.
That means
right.
If I only sketch this curve, you know, only this curve, because you know from here it is decreasing. It has to be. That means, you know, at this point, you know, before this point it was increasing, and at this point it was decreasing. That means this is the maximum, and you know, at the maximum point the derivative must be 0. So I had to start from here. So this is our starting point. Okay. And after this point, I know it has to be negative. Okay, so it should be negative. It must be below x-axis. Okay, and then, you know, at this point, it has to be 0 again. So the thing is that, you know, in the beginning, it was decreasing, but the rate of decrease, the rate by which it was decreasing, it was increasing. You know, the rate was increasing. As you can see, at 180 degree, the rate is maximum. The rate of that means the derivative would have a maximum value or the minimum value. You know, if you think about in terms of magnitude, at 180 degree, it has to have the maximum magnitude of the derivative. That means it should be something like this. You see, at 180 degree, let me show you here. Yeah, at 180 degree, you know, it was the value of the derivative is maximum. Of course, in the opposite direction, because the rate was, it is decreasing, it has to be negative, but the magnitude is maximum. Is that clear?
Yes, it makes sense. Now I got it.
Yeah, perfect.
Thank you.
And of course, no problem. Thank you for asking, by the way. So yeah, so do ask whenever you have question. Yeah, it is really going to help us and others. Thank you, Hujista. Okay, and of course, so this is the derivative, you know, in between these two interval. And again, at this interval, the rate was maximum. The rate of decrement, it was maximum. That means the derivative must have a maximum value. Or I mean, when I say maximum, it can also be minimum. You know, I'm talking about in terms of magnitude. Okay, yeah, and then this is actually a cos curve. So again, don't take my word for as granted. You know, you have to ask why it is a cos curve. Of course, there are many other functions, but there are some other reasons also. Okay. Let's move on to a cos function. And again, you know, be more attentive. Maybe you can also try to find a derivative function or curve yourself. So just to be more, just to clear your concept further. Okay, as Vikas is saying, but the change is decreasing as the angle is increasing. I think, yeah, during that interval, the change is increasing, not decreasing in that interval. Okay, so let's do this cosine thing. I mean, it's the same idea. Actually, sine and cosine, they are the same, you know, kind of functions. Only they are shifted by some phase angle, and that's it. Okay, just a second. Okay. Do you see my screen, by the way? Something just changed. Can you see my screen? Hello? Yeah, okay, thank you. Somehow I lose. Just give me a second. Where is that? Okay, no problem. Okay, so first thing first, you know, when we want to find the derivative of cosine function, we are going to start from the minimum and maximum point. Okay, so how many or actually let me call them extreme points. Okay, so when you say extreme, it can be minimum or it can be maximum. How many extreme points we have in this curve? So we have 3, right? Yeah. So first point is here, the second one is here, and the third one is here. Okay. That means at these 3 points, we are going, the graph, the derivative graph must be 0. Okay. So the graph is going to pass from this point and this point and this point. Okay. So these 3 points, let me make it even bold. So the graph must pass through these three points. Okay. So let's try to think between the first minima, this point and this point, how the graph is changing. So again, it is decreasing. So it has to be negative. You see, it is decreasing, but in the beginning it was decreasing with a bit slow rate, but at some point the rate was fast enough, then the rate was decreasing again, so it became 0. So that means during this actually interval, the graph has to be negative. That's for sure. It has to be below x-axis. So actually, let me also define this way. If you want to make a curve between these 2 points, such that the curve remains below x-axis, and it is a smooth curve, because the cosine is a smooth curve, so the derivative has to be smooth curve. So there is only one option. Sorry. So there's only one option. Basically, you have to sketch the graph like this, because if you want to start, it will go down, then it has to come up, because you want to reach the 0 again, right? And again, when the graph was at 90 degree, the rate of change was the most, right? So that means the derivative has the highest value at this point. Okay, so after this point, between like in this interval from 180 to 360, the graph is increasing, as you can see. That means the graph has to stay positive. So in order to stay positive, and by the way, at this point 270, the graph has to have the maximum value. So let me even draw this point also. So the graph has to pass through this point and this point. So this is the one of the way actually. Actually this is the only way if you want to make the curve smooth. So this is how a smooth curve we can make. If you try to make any other curve, it won't be not as much smooth. So this is the smoothest curve I can say, because the function itself is quite smooth. So the change has to be also smooth. So it shouldn't be like a modulus function, or there shouldn't be any sharp turns and so on. So it has to be like a very nicely and very well behaved function. So can you realize what is this function, this derivative? It looks something like a sine, right? Is 10? No, it's not 10. 10 actually, 10, I told you, tangent function is not well behaved function. It's very, very, it behaves quite, yeah. So I got an answer, and yeah, Vikas is saying it's a sine actually, but yeah, it's minus sine. So it's actually not sine exactly, because sine is something like this. It is minus sine. So it's you have to flip it on x-axis. So that means the derivative of cos x is minus sine. And basically you see this kind of formulas in your formula booklet, and you might have memorized them. So do memorize. I'm not saying don't do that, but also try to understand why is that so, because once you understand the concept, then you will be able to find the connections between many different mathematical quantities. And by the way, that's the ultimate, I can say that's the ultimate learning process, if you're able to find connections. Okay. Even though this might look very simple and trivial, but once you think deeper, you will see, once you find the connections, it's a very huge, like a unification is something very tremendous, very big thing actually. For example, like Abdul Salam, the physicist, Pakistani scientist, he unified 2 different forces of nature. Okay, that's the quest of the scientists. They want to unify different, apparently seemingly different things. So for example, electromagnetic theory, for example, electric field and magnetic field, and quantum physics and relativity, the people want to combine them. So there's always, the unification process always happening, and to be able to play our part, we have to be innovative. We have to understand the very concept. All right, so we have learned the polynomial functions and trigonometric functions and so on. Actually, since you asked, I was not planning to show you the tangent function, but actually let me quickly show you. Okay, let me not show you because this was actually the thing we discussed earlier in the previous session, but let me simply tell you the derivative of tangent function is second square x. And it might look quite weird, but actually we're going to learn some couple of rules, and from there we can also derive it. Okay. Yeah. So let's move on, because actually, like generally, sine and cosine, they are important functions. Why? Because the curve is quite smooth, and the nature, whenever you make a mathematical modeling of the natural phenomena, since the nature is quite smooth, so generally we use sine function or cosine function. Okay. The tangent function, you will rarely see them in nature. That's why it's not that much important. Okay, the last bit of the derivative is about the exponential and logarithmic function. And actually we discussed them earlier in our sessions, why the graph looks something like this. So, but this time we are going to focus on the derivative. So you might actually even know, just a second, you might actually know wait a second. Okay, so you might know basically how the graph of the function looks like, but let's discuss about the derivative. So first thing first, we learned that we have, whenever we want to sketch the derivative function, we have to start with the maximum or minimum point. Okay, but if you look, the first function is the exponential function. As it is 2 to the power x is exponential function. So is there any minimum or maximum point of this function? Yeah, so there's no actually minimum or maximum point. So there's no, right? So basically it starts from here. Actually, even though it looks like it is going to 0, but if you zoom in further, this function never touches the x-axis. It never crosses the x-axis. That means we call them asymptote. Asymptote mean it continues forever. If you go on the x-axis, not undefined. What do you mean undefined? So if you continue from the negative x-axis, you will still not be able to connect or touch the x-axis. So we call them asymptote. So the thing is that the function is it is increasing from, if you come from left to right, you see it is increasing. And by the way, the rate is also increasing, as you can see here, right? It is increasing and continues increasing. So it's a function which is always increasing. That's very interesting, by the way. This is a function which is always increasing. That means the derivative must be always positive. Okay, so it has to be always positive. So there's only what kind of function. So if I ask you to maybe make any sketch which is always positive, so how can you make any sketch? So for example, like maybe you might think, okay, I can make something like this. Yeah. So let's say the derivative is something like this. It is always increasing, as you can see here. The derivative, maybe is positive, but actually, saying linear line. Yeah, I mean that seems true, right? It seems true because it's positive, but there is actually two problems. The first problem, actually, this curve, the function actually, it is a continuous curve, right? When we say continuous, there's no break. It goes on and on and on forever. So that means the derivative must also be continuous. Is that clear? If it is continuous, then the line must not stop here. It has to continue, right? Like this. And now we have a problem. If the line continues, it becomes negative, right? Let's say after this point, it becomes negative. That means the function is, if the derivative is negative, that signifies that the function is decreasing. But that's not the case. Function is never decreasing, as we learned. Function is always increasing. Okay, you see the problem? This was the first problem. Actually, let me quickly show you on the GeoGebra. Okay, let me just try. Sorry, just give me a second. So let me quickly sketch the graph so you will see what is happening here. Let's see. 2 to the power x. So you see, this is the curve. But if you zoom in, if you go inside, you see, if you zoom in further, it never crosses the x-axis. You see, There's still some gap, still some gap. If you zoom in, you see there's still some gap. That means the function is always increasing. So if it is always increasing, the derivative must be always positive. But now, as you can see here, we have an issue, very serious issue. If we find this as a derivative, so this is because this derivative is also function. The derivative function is decreasing. So can you fix this? Oh, okay, we will try to fix this one. But this is also one more problem. Can someone also indicate what is another problem with if this is the derivative of this function? There's also one more issue with this. So can someone point out, or maybe someone want to say anything about it? Yes. Rate of increase, Hasan. Nice. Thank you, Hasan. Can you, that's actually quite true. Can you elaborate what you mean by this? Yeah. Okay. Thank you for this. You also got the idea. So it is increasing, but in this case, if it is a straight line, then the rate of change is a constant. But the thing is that the function is increasing with ever increasing rate. So that is actually not possible. This is not the derivative. So we have to think maybe carefully. So maybe if you try enough, we can find out another nice or the real function. So it's going to be something like this. I'm sorry. It's going to be. It will be something like this. It will start from here. Actually, let me change the color. This one. So it will start from here. I mean, it's something like it's a kind of a same exponential function. So actually, if I make a sketch of the function e to the power x, so the derivative, if we have e to the power x instead of 2, e to the power x, the derivative of this function is going to be itself. Okay. By the way, this is the only function in the universe which is self-derivative. Okay, so that means the exponential function, especially when you have the base as e, and e is the base of the natural logarithm. Is a irrational number. It's like a pi. We know pi and e and phi, all those things. So remember the derivative of exponential function e to the power x. The derivative is itself. So it is increasing. The derivative graph is the function itself. Okay, and now you understand the idea. Why is that so? We can also prove it. What does that mean in words? That the function itself represents state of change. Yeah, it's actually, what does it mean? It means, it is changing, and the rate of change of the function is the function itself. Yeah, it's a very strange thing to say. And that's why, honestly, if you, like whenever actually you think of any phenomena, okay, since you asked, Khujista, by the way, thank you very much. Let me discuss quickly what exactly some applications of it, right? So for example, like, think of any function in the universe which is changing. I mean, actually everything is changing, but if you think of anything which is changing like naturally without any interruption from human side or from other side, generally expansion of the universe, okay, but expansion, it's the extreme limit. Since you don't know the nature of expansion very well, that might not be, I think, the case. But for example, what can we say? Maybe the evolution of something, or maybe, for example, like, if you pour the carbonated water, let's say Sprite or Coca-Cola or whatever, on a glass, and you see there's a foam, right? The foams, there's some foam on top of the surface of the liquid. And since, like the foam, that depends on the quantity itself. If you pour more Coca-Cola or Sprite, there will be more foam, right? And if you give them some time, the rate by which the foam is decreasing if you make a curve, it is going to be an exponential curve. Okay. Similarly, what else can it be? So for example, like, you know, if you, okay, or if you throw, let's say, if you have a, let's say 1,000 dice, you know, the dice, the chekka we use to play the Ludo. Let's say you have 1,000 of them and you throw them, right? And you simply take, you know, if you get 6, you take those dice outside. So if you, you know, and then you throw them multiple times. So once you make a curve, like how many 6 are thrown away, then the curve which is going to be made is going to be an exponential decrease. Okay. Similarly, for example, like in radioactivity, which is also a natural process, radioactivity, there is also ln or e to the power something. Speed of a virus, exactly. You know, the splitting of bacteria, perfect. Thank you. Because, you know, they depends on the initial numbers. So the more the bacteria you have in the beginning, the more they are going to increase. So the increment, if you want to make a plot or the graph, you will see the increment is exponential, and also the speed of virus, how fast they can move around. So it's also exponential. So actually, most of the things which is happening in the universe, they are exponential growth. Okay, it's very interesting, by the way. Okay, so let's move on to the next thing. Half-life, yeah, is decreasing exponentially. Exactly. Actually, half-life, and also, you know, if you also all the natural phenomena, for example, in chemistry, you study the rate of reaction. Maybe you will see in the A levels or FSC or other system, the rate of reaction. You will also find there's some kind of exponential thing going on there. Even, you know, like those sound decibels, the sound intensity. By the way, we use log there. Log is also kind of exponential. They are the same thing, right? So this is just a different perspective. So log decibels, the sound intensity, rate of reactions, and even the earthquake, the magnitude, you know, those the scale we use, the 6 magnitude or 7 magnitude, they're actually on the logarithmic scale. So they're also exponential, by the way. I think now you get the idea. So exponential curves they're very important in nature. So if you're studying especially the natural sciences or engineering, you will always encounter with E, by the way. And that's why we use, you know, here, even though here we have log x, but like generally we use ln x, yeah? So ln x, this is actually the same thing as log with base E. And we discussed log in the previous session. Okay. So now the last function we have in our hand, and we have to unlock or understand the graph of this guy, logarithmic function. So maybe some of you already know the formula from the formula booklet, but let's try to understand what is happening here. So are you ready, guys? So let's go for the adventure. And I told you this is our last function. So what is happening in this function in this case? Yeah. So in this case, the function is increasing, and it is always increasing, right? So it always increases. Increasing, but at a decreasing rate. Perfect. So what kind of function we can make as a solution, as a derivative of this function? So the function has to be positive. Of course, it is, because since it is always increasing, the derivative must be always positive. But since the function is increasing at a decreasing rate, so the derivative must be getting smaller and smaller. It's going to be closer to the x-axis. So what kind of function you can make? And as you can see here, this is not going to be a linear function, right? It's not a linear relationship. So I want you to maybe sketch a function on your notebook, which is positive, always positive, but it is decreasing. Let me give you maybe 30 seconds. Make any sketch, whatever comes in your mind. So 2 conditions. It has to be positive always, right? Second thing is that as you go in the x-axis, the value of the function is going down and down. Yes, what kind of function it could be? Okay, you have 20 more seconds. Mirror image of this function, but like it works. mirror image of this function. Okay, something, okay, yeah. But actually it's not e to the power x, interestingly, in this case. Let me sketch this one. It is going to be something like this. I hope, sorry, I hope you have done this already. So let me do it now. Not the red one, but let me change the color. Yeah. So it is something like this. This. Okay. You see this curve? 1 over x ln 3. Yeah, exactly. So basically, you know, to be honest, this is actually something 1 over x kind of thing. No, there's also some constant you have to multiply, but it is essentially 1 over x. And we call this function as, and even remember, this is not actually exponential function, you see, because you know when it goes to 0, it becomes infinity kind of thing. So can someone tell me what is this function? What do we call this function? 1 over x. It has another name. It is also called hyperbola. Okay, 1 over x is a special case of hyperbola. But you don't have to know this thing for now. So that means, you know, if you have a log x, so let me simply make the rule here, write down the rule. So the log x, the derivative of log x is equals to 1 over x. But you know, if it is not ln x, if it is not ln x, if it is log x, then the derivative is a bit different. I'm simply focusing on the ln, like a natural log or e to the power x. As you can see here in this case, whenever you have e to the power x, the derivative is itself. If you have ln x, the derivative is 1 over x. But if you have something else, let's say 2 to the power x or log with base 3 or base 10 or base 7, then the derivative changes a bit, in a sense that you have to simply multiply by some constant. Okay. And for that, you know, I don't want to actually write down those constant, but of course you can simply readily find out from the formula booklet. Okay, but I think now you get the idea what is the meaning of derivative and how we can find out the derivative from the graphs. Okay. All right. So before I move on, so this was actually the overall idea, how to find the derivative from the graph. Next, we are also going to find the derivative. Maybe I will do some 1 or 2 example from algebra. You know, that's also important just to see, just to compare. That means, you know, from 2 different paths, they take us to the same output, the same result. So before we move on, I just want you to let me know if you have any question. Yeah, actually, Khujista is asking a very nice question. What's the difference in nature of the derivative graph if the base is different? So, you know, if the base is different, since, you know, when we say ln or the natural logarithm, by the way, ln means it's a natural log, natural, and e is also natural. So then the derivative is simple. But if it is not, the base is not e or base is something else, then I told you have to multiply by some constant. So in this case, actually, let me just let me tell you, if you have, let's say, base 2, so if you have log 2x, yeah, and if you want to find the derivative is going to be 1 over x again, but then you have to multiply this thing by some constant. Okay, so in this time, actually, in this case, the constant is going to be you know, ln2. You know, ln2, like, you know, this was the base, so you have to multiply by or divide by this constant just to fix you know, the change. Okay, so but that's not our focus right now. So you always have to multiply or by some number to fix the thing. But if it is a natural log, it is going to be straightforward. Okay, so the rule actually is that if you have any base, let's say instead of 2, if you have a base n, let's say here I can write n here, so you will simply multiply by ln n. That's it. But these things you can easily find on any textbook. So there's, and it's not actually that much important maybe concept wise. So let me move on. Okay, so let's try to find the derivative from the boring way. I mean, not boring, but from the theoretical way or from the first principle. just to show you the power of the graphical way to find and also the from algebraic way. Let me know if you have any question from the graph things, and then I will move on. Anyone? Okay, let's move on then. So let's try to find out the derivative of x squared. Okay, we have function x squared, and we want to find out what's the derivative of the function x squared. Okay, of course, in the previous slide we have seen how to find the derivative, how to find the derivative of this curve from the graph, making it's going to be a straight line. But let's try to use algebra. Since we know that the derivative actually we started from the slope. If you remember from our first session, we discussed that the slope actually gave us the change in the function. So we can use the same idea and we can extend them. The only thing is that to make the slope as a derivative, we have to make the change, this x2 minus x1, very, very small. So I will do that. So let's, the same thing, y2 minus y1 over x2 minus x1. So I can also replace y with f of x plus delta x minus f of x. If, let's say, if we have 2 points, let's say point 1 and point 2, and if you want to find the change in between these 2 points, let's say, so let's try to find out the slope of this curve. Even though it's not a straight line, it's going to be a curved line, but we will fix this later. So let's start with this idea of this function f of x plus delta x minus f of x. So it's the same thing as slope. So instead of writing y2, I am writing f of x plus x. So if the function is x squared, how this thing will change, this thing. So let me write down here. This will become x plus delta x, okay, squared, right? Because the original function is x squared. So I'm simply going to replace x with x plus delta x minus, then we had actually f of x, yeah, which is x squared. So I'm simply going to write x squared. I'm going to divide this by delta x, okay? Because x2 minus x1, the denominator here equals the x. So this is actually like the slope formula. This is how we find the slope. This is y2 minus y1 over x2 minus x1, which is delta x is x2 minus x1. So let's try to simplify this further. X plus delta x squared. So we can simply use the formula. The square formula is going to be x squared plus 2x delta x plus delta x squared. Okay, so this is how we can expand the bracket, yeah, this bracket. Then we have minus x squared. So this x squared is this one, right? Okay, then divided by delta x. Let's try to simplify this thing. X squared, by the way, as you can see here very quickly, this x squared and this x squared, we can cancel them out. Okay, so I'm simply left with 2x and 2x times delta x. I'm sorry for this, and plus delta x squared over delta x. Okay, and let me also, since we are dividing by delta x, let me divide both terms. We have 2 terms on the numerator. We can split them, right? So this will become 2x delta x over delta x plus delta x squared over delta x. And of course, as you can see, we can cancel delta x with delta x, and this delta x with a square I can cancel. So this becomes actually, let me write it here, 2x delta x, sorry, 2x, not delta x. So this becomes actually 2x plus delta x. Okay, so this is the slope of the function at these 2 points. Okay, if you remember, to go from slope to the derivative, we have to do something, because the slope is defined only for a straight line, right? And as you can see here, when we have this function, this line is not a straight line, it's a curved line. So to minimize the error, to make sure that we are actually finding the slope of the function, what we can do, we can simply choose these 2 points very, very close to each other. That means if we make the second point, this second point close to x, so that means x2 minus x1, if it is equals to 0 or close to 0, that means we can simply reduce the error caused by the curved nature of the function. So what actually I will be doing, I'm going to simply apply the limit. If you remember, the derivative we have defined this way. So the dy over dx was defined as limit delta x goes to 0 and f of x plus delta x minus f of x over delta x. Yeah. That means actually simply we have to apply the limit here. So limit delta x goes to 0. Then it will become the derivative. So the dy over dx when delta x goes to 0 and we have 2x plus delta x. And once, like in the case where delta x goes to 0, this becomes 2x. That means the derivative of x squared is 2x. Yeah, again, it's a straight line. We have already seen in when we sketched the graph, but at that time we did not know if it is 2x or 3x or 1.5x and so on. But now we know the derivative of x squared is 2x. Shall we do the same thing with this exponential function from the first principle? Okay, maybe let me do this thing very quickly. So since we know the derivative, if you want to find dy over dx, this is defined as limit delta x goes to 0 and f of x plus delta x minus f of x over delta x. So actually, this thing actually is a slope. This is actually the definition of slope. So the slope becomes derivative whenever you have the interval very, very small. So let's try to see what is happening in this case. If you have the function e to the power x, so the limit, again, we have it here, delta x goes to 0. So e to the power x plus delta x, okay, minus e to the power x over delta x. And I can write this as limit again, e to the power x times e to the power delta x. So you see, if you have plus sign, I can write this guy like this, yeah. So they're the same thing. We can split the power, because a to the power b plus c equals a to the power b times a to the power c. So I hope you know this exponential rules, okay? Minus e to the power x over delta x. So let me write limit again here. And e to the power x, if I take this common outside, I'm left with e to the power delta x minus 1. And of course, the limit is about delta x, so delta x goes to 0. So as you can see here, we have delta x here, and this one actually is e to the power x. There is no delta x here. Let me take this guy outside, e to the power x outside. And we can apply the limit delta x goes to 0, e to the power delta x minus 1 over delta x. And this is a bit tricky. We discussed this earlier. We have to see this actually on the maybe GeoGebra. We can see, when the e to the power delta x goes to 0, so this becomes 1. So 1 minus 1 is 0. But then we also have in the denominator, this is also 0. So we have 0 or 0 form here. And we have to actually, there are different rules. We can use the L'Hopital rule and other rules we did not discuss. You will see them in higher grades. But you can see if the rate of the near 0, if they're together, then this equals 1 because they cancel each other. So let me quickly talking about slope. Link, I don't know your name, but I will answer you. I will answer you in a while. Let me just simply show you what the curve. So I have e to the power x, e to the power x minus 1, and we also have another curve x. So if you simply divide g over h, let me not even do it. Let me just show you. So as you can see here, not this one. So the blue function is, the blue function is the numerator, the top function, and the red function is the denominator, like delta x. As you can see here, if you zoom into the to 0, as you can see here, when you go close to 0, both functions, like, they overlap, right? So when they overlap, actually they are going to cancel each other. Maybe we don't know exactly at point 0, but that's the idea of the limit. We don't actually know, we don't want to know what is happening at that particular point. Instead, we want to know what is happening nearby that point. So as you can see here, near 0, don't look at 0, actually, there's no need to see at 0, but before 0, the functions are somehow, they're equal. That means this is going to be equals to 1. So e to the power x, and once you apply the limit here, this will be 1. And that is equals to e to the power x. That means the derivative of e to the power x is e to the power x itself. Clear? This is actually very interesting. Actually, if you go to the university level or maybe higher level, once you find the limit of this thing, they maybe tell you different rules. But I personally don't like them much. I mean, of course, I do like them, but it's good to see from the graph, like, what is happening. Okay, so this value 0 over 0, even though it was 0 over 0, if you put x delta x equals 0, but that actually essentially equals to 1 as x goes to 0. Yes, Sujista, yeah, it is equals to 1 because they overlap. If they don't overlap, then it's not equals to 1. Maybe it might be equals to 0. Sometimes they can be equals to maybe infinity, and so on. Can we use Taylor series to simplify the numerator? Yes, actually that's what you do. Maybe since this course is mainly for the high school students, they don't know much about Taylor series, so we don't discuss. But the thing is that, again, if you do the Taylor series, generally we don't want to focus on the concept. We simply lost in algebra, right? We just do a lot of calculations, and we came up with this idea. But it's very important to understand what is happening. So yes, as overlapping makes them both equal, right? Yes, and the operating, yeah. So since they're equal, so we can cancel them. So again, remember, what about at equals 0? We don't know at equals 0, but we know before 0, like nearby 0. This was one more question. Let me see. I'm a bit late. In last slide, when you put value in f of x, you never put value of y. I don't understand exactly. Maybe if you can repeat your question, I can understand. Yeah, I'm sorry. Yeah, let me actually show you this thing. Let me show you the graph of this one. When we divide these two functions together, g over h, you will see at point 1, you see if I zoom in point 1, there is actually a discontinuity. You see this circle here. That means the graph is broken at this point. I mean, broken means we don't know exactly. Like, no one knows actually, to be honest. But we are only interested in when we go close to this point. It is as if we are approaching 1. So that is the very idea of the limit also. We don't know what is happening at that point, because by nature, the math is not that simple also. So there's infinity and so on. So exactly at that point, you can say 0 over 0 is not defined. That's called indeterminate form, but it works for us because we can only understand the values nearby that particular point. Okay, so even if you zoom in, you just understand, okay, it is going to be 1. Undefined right, that's the limit. It's called undefined right, that's the limit. Actually, it's not called undefined, it's called indeterminate. Undefined means we are unable to define them, but as you have seen, we are able to define them. Yeah, that is equals to 1. That means they are defined at that point by mathematical, by the limit. I mean where the limit ends. Yeah, actually, like again, at that particular point, on that point, we don't know what is happening. No one knows actually, but the limit is defined. Okay. Okay. Actually, I just realized, since you have a lot of questions about this, we can continue to find the derivative of sin x also, because there we will also use this very idea of the limit. And actually, in this case, you will see we will have 0 over 0 form, but in one situation that will be equals to 0. In the other situation, it is going to be 1. But if we do that, we are going to skip the next thing. Let me still do it, because let's try to find a sin x derivative of sin x from this algebraic method. Again, I'm doing it because this is also going to make you understand the nature of limit and so on. Okay, so be with me. Let me do it. Just give me a second. I have to add another slide. Keep. What is that? So now actually we have this function y equals sin x. Okay. Before actually I continue, I also want you to understand or remember, maybe some of you know or some of you don't know, maybe if you have a compound angle a plus b, we call them compound, means there are two angles. So the formula for this is also a derivation, but we are not interested in the derivation. Let me simply tell you the formula: sine a cos b plus cos a sine b. Okay, so keep that in mind. We are going to use this formula here. So let's try to find the derivative of this guy. So dy over dx here we have, and f of x plus delta x minus f of x over the change in x, right? So change in x is delta x. So on the top we have the change in y, which is f of x plus delta x minus f of x, and in the denominator we have change in y. But again, that's not the full story. We have to put the limit sign here if you want to find the derivative. So derivative limit delta x goes to 0. So by the way, so this guy make the slope. This is the slope of the second line, but this guy, when you put the limit, this make that second line to the tangent line, by the way, or it is how we define the derivative. Actually, one of you also asked me the same question. So I think when we solve this problem, your question will also be answered. So please be with me. Okay, let me continue. F of x plus delta x and minus f of x. So here we have sine. The function is sine. So this is going to be sine of x plus delta x minus sine x over delta x. And of course, there should be limit. Delta x goes to 0. Okay, I'm going to simply write down, I have to expand this, there's a compound angle, x plus delta x. I will use the, this compound angle formula. Sorry. So the limit sine x and cos delta x. The delta x is the second angle, by the way, and plus cos x times sine delta x. Okay, so this is how we expand sine x plus delta x, and of course we have minus and sine x. Yeah, so this sine x actually is the same as this one. This sine x and this sine x are the same thing, and we are going to divide by delta x right now. So we have limit delta x goes to 0, and we have to simplify. As you can see on the numerator, we have a lot of, actually we have 3 terms, and we have to simplify. So how we can do it, as if you see here, we have sine x here, we also have sine x here at the end. So let me use these two terms. You see we have 3 terms: term 1, term 2, and term 3. By the way, the terms are separated by plus or minus sign. So let me take out the sign as a common quantity from these two guys. So this I'm left with cos delta x minus 1, okay, and plus cos x delta x, okay. And since I have to divide this also by the delta x, let me divide this separately. I can do it, right? I can split the these two guys. By the way, this is not delta x, this is cos x. I'm sorry, where is this thing? Cos x sine delta x. Okay. So cos x and times sine delta x over delta x. You know, now we have two terms. We can apply the limit separately. Okay. So we have term number 1 and term 2. We can apply the limit separately. What I mean here, what I mean actually is this. If I simply write here limit delta x goes to 0, you know, this in this term, the sine x, I can only write the delta x term inside the limit. I can move sine x outside. Actually, let me erase this thing very quickly. Let me do this thing. Yeah, I will take sine x outside. So remember, this is very important. I can take sine x outside because the limit is only for delta x, not for x. So it is going to be limit sine x times limit delta x goes to 0. We have cos delta x minus 1 over delta x. Okay. Plus limit. I can, you know, split the limit separately. But before I do that, actually, I can also take the cos x outside. Okay, because the limit is going to be applied only for delta x, not for x. So sine delta x over delta x. Yeah, so actually now the thing is that we have to evaluate this guy and this guy. If you remember in our previous session, we have discussed both the cases, but let me do it again very quickly. So let's try to think about sine x over x. You know, even though we have delta x, but delta x which goes to 0. Let's try to sketch these two curves and see what happens when we have sine x over delta x, and what happens when we have cos x minus 1 over delta x. Okay, so let me very quickly, actually, let me remove them. I'm going to write here sine x, sine x, sorry, sine x. Yeah, and then we also have sine x over x. So this one thing. Yeah, and if I find the ratio, so basically q over r, so q divided by r. So yeah, as you can see here, you know, if you go to this function sine x and y equals x, they are again the same. When you go close to 0, they are overlapping. That's why they will be cancelled out, and the answer is going to be 1, which you can see from this curve. You see the derivative. So the ratio sine x over x is 1. But if you click here, it says removable discontinuity. It means there's a discontinuity here. The graph is broken, or I don't know. The graph is, we have no idea what is happening at that point. But we know for sure that when we go close to 0, the value of the graph is going to be 1. But what about the case for this guy, cos x minus 1 over delta x? Sorry, cos delta x minus 1 over delta x. So let me also try to sketch these two graphs. So I have here cos x. We also have x. Sorry, that was not the case. It should be cos x minus 1, yeah? And 1 x. So now, as you can see here, if I divide these two, yeah, even if you see from these functions, cos x, when you go close to 0, they're not overlapping, right? But instead, cos x goes to 0 before, I think much way earlier than y equals x graph, before this orange graph. That means the numerator here, in this case, the numerator is going to be 0 way faster or way earlier than when delta x goes to 0. So essentially, when delta x goes to 0, this becomes 0 first, and this becomes 0 later. So essentially, this becomes something 0 over something, which is 0. Okay, we can also see if I plot these two graphs. Let me simply divide t over f1. So you see, it is 0. Even though there is a at the particular 0 point, there is a discontinuity, but it goes to 0. That means this will be 0. when limit delta x goes to 0. And this is going to be 1. And that means sine x times 0 is going to be 0 plus cos x we have in the second term times 1. So that will give us cos x. Now we know that the derivative of sine x is cos x. We also saw it from the graph, but from the algebra, we can also see it has to be a sine, it has to be cos x. Okay. Any question or comment on this? Thank you. Okay, we have 4 minutes. If you allow me, I can take some more time, but let me know if you have, for any reason or whatever reason, if you want me to finish by 3:30, maybe if there's any one person who wants me to finish by 3:30, I will finish, yeah, because that's your right. But if you are willing, we can continue for some more minutes. Okay, the next thing is the derivative power rule. And you got the power. So basically, thank you for Gista. So actually, if you have x to the power n, and if you want to find the derivative, this is how it works. We discussed already, you know, we found the derivative of x squared was 2x. So let me give you some examples. So if you have x cubed, and if you want to find the derivative, this will become 3 times x squared. So you make 3 as a numerator, and then you make power 1 less. Yeah. So you also have seen it from the graph. So for example, if you have x to the power 7.5 even, it doesn't have to be a whole number. So the 7.5 would become the coefficient, and x to the power 7.5 minus 1, 6.5. It's actually a more interesting things from here. What about x to the power? What about 1 over x? Sorry, 1 over x. So for 1 over x, I can also write this as x to the power minus 1. So the derivative of x to the power minus 1 is going to be minus 1 times x to the power minus 1 minus 2. So minus 1 over x squared. So this power rule actually we can apply in many places. The last thing actually, what if we have x7? What's the derivative of 7? We know since 7 is a constant, the derivative must be 0. But we can also use the power rule, because power rule is very powerful. You know, I can write 7 as 7 times x to the power 0, right? Same thing, because x to the power 0 is 1. So I can write 7 as 7 times x to the power 0. And if I use the power rule, so 7 would be there. And you know, the 0 would become the coefficient. So 0 times x to the power minus 1 or whatever. But since you're multiplying by 0, the whole thing would become 0. The whole thing collapses. That also means the derivative of a constant function is 0. And the derivative of x is 1. You can see from the power rule. The product rule, actually, I was planning to discuss this product rule graphically, but I think for now you can just simply memorize, or not memorize. Yeah, memorize. You have to. You can look at here. If you have two functions, u times v, this is how we find the derivative. First function times the derivative of the second function, and plus vice versa. Maybe in the next session I might spend more time, but yeah, let's see. Yeah, let's not discuss. You know, I was planning to describe it as a graphical way. But if you really need explanation, do let me know. I can find a way to help you out. Okay. The quotient rule is something like this. Actually, these rules I'm skipping them very fast. The reason again, because you can find easily on in your textbook, and you can find many practice questions. So you can do that. We can focus on the main thing. Oh, sorry. You don't see my screen. You don't see my main screen. Wait a second. Yeah, thank you for asking. Because okay, the chain rule, I think you have seen this chain rule, but what actually is happening here, this is very interesting rule. And I see, honestly, in many of the books you are given lots of formulas and, you know, this and that, but the concept here is very simple. And once you understand this concept, you can very easily solve very lengthy questions and maybe very complicated questions. You will see. Actually, this is actually a really Yeah, let me discuss this first, the chain rule. And this is very essential rule, by the way, very important. You will encounter them so many times. And honestly, most of the books, the way they teach is very complicated, even for me. So I will try to make it a bit more simple. So the idea actually here is that, let me just tell you one thing, once we find the derivative of what is happening here, the derivative of, let's say, x to the power 7, for example, I told you that the derivative is going to be 7 times x to the power 6, yeah? But the thing is that we should not stop here. We have to continue. We have to multiply the derivative by the inside function or innermost function. So, innermost function in this case was x itself. So we had x to the power 7, but inside function, if you zoom in, if you look into the function, the innermost function was x. And what is the derivative of x, by the way? We have learned in the previous slide. The derivative of x is 1. So I'm going to multiply 1 also. I mean, you might ask why there's no need to multiply by 1, because the thing will remain the same. But there is a reason I'm telling you. So again, of course, the answer is going to be 7x to the power 6 again, but you have to multiply by 1. Let me give you one more example, and then you will see what is happening here. What is that? Let's say x to the power 11.5. Okay. So if you want to find the derivative of this function, this is going to be 11.5. The power would become the coefficient times x to the power. We have to subtract 1 from the power, which is going to be 10.5. Okay, but I will not stop here. I have to multiply, I have to continue until I reach the inside function. So in this case, again, the inside function is x, yeah? And what's the derivative of x? So remember, the derivative of x is d over dx of x. Actually, it is 1. So remember this thing. So inside function is x, and the derivative of the x is 1. I'm going to multiply this by 1. Okay, perfect. Okay, if this is the case, let me ask you one question. What is x here? What do we mean by x, or what does x represent? Just be with me, because you will learn something very interesting. Yeah. Yes, anyone? What does x signifies here? So yeah, x is a variable, right? So that means x can be anything, because it's a variable. It can change its values. X can be 7, x can be 9, x can also be x cubed, x can also be x to the power 7. So it doesn't matter, x, we can replace x with anything. Okay, remember, and that's why we call them, yeah, it's a value. So it can be anything. It can be a constant value. It can also be another variable. Okay, so for example, if I ask you the derivative of x cubed, and simply the derivative of x cubed is 3x squared. So in this case, x can be anything. It can be any value. It can also be any function. It can also be anything you want. It can be anything. It's up to you. It can even be like this. It can also be a happy face. Doesn't matter. And if you find the derivative, you get 3 times. Yeah. So it's up to you how you define x. Okay. So just be with me. This time, we know that the derivative of x cubed is 3x squared. Now let me say that x is sine x. X can be anything, right? X can be y, sine x, log x, or whatever. So let me say I'm just simply replacing x with sine x, and same thing, yeah. And if I want to find the derivative of sine x cubed, what happens? So if I want to find the derivative, so basically, even though we have sine x and we have no idea, x can be anything. So what I will do, I will simply consider x as sine x, and I will simply use the power rule. So the power rule says that the power, here we had 3. So this would become the coefficient times x, but in this case, x is sine x, doesn't matter. X can be anything, squared. Okay. Okay. Then what we will do, I told you the chain rule says that you don't stop there. You have to multiply by the inside function. So in this case, what is the inside function? Sine x, yeah. And what is the derivative of sine x? is cos x. So I will multiply by cos x. And that's how we find this is the derivative of sine x whole cube. I think it's time for us to have a more example. I have to add more slides here. Okay, what is this? Sorry, let me. Okay, let me give you one more example. Let's say we have e to the power sine x now. You see, this is a very interesting function, and I want to find the actually not even this one. Let me use another example first before I move on to this one. So what we have y equals sine x cube plus 3x squared or 2x squared. Okay, and then we have the whole thing as power 7. So you see, it's a very complicated functions it looks, and if you want to use the chain rule and all those things, it becomes very complicated. But we know the very idea. Since we have a power here, you see the power, we know for sure that we are going to use the power rule. Okay, so the power rule says that if you want to find the derivative y prime, so the power rule says that this power would become the coefficient. So let's make it a coefficient, and I will continue. I will simply write down the x, but in this case x is sine x cube plus 2x squared. Doesn't matter, x can be anything. So we have sine x cube plus 2x squared, right? And then the whole power 6, because we have to subtract 1 from the power. All right, and but that's not the full story. We have to continue. We have to multiply by the inside function. So what is the inside function we have right now? We have sine x cube plus 2x squared. So the derivative, what is the derivative of sine x? Is cos x. And again, you know, when we say the derivative of sine x is cos x, so x can be anything. In this case, x is x cube plus 2x squared. So I will multiply simply by cos x. Yeah, but x is x cube plus 2x squared. Okay, so step by step. But then, you know, that's not the full story. We have even further inner function, inside function, or the inner function. So the inner function is x cube plus 2x further. So I will still multiply them once more. So once I multiply, this would become, once we multiply with the derivative of the inside function, 3x squared plus 4x. So this function actually, this is the derivative of this function. So we just continue multiplying until we reach the inside function. That's what I meant when we discussed these things. Yeah. Okay. Let's do maybe one or two more questions. You know, here we have, maybe I will also assign you this thing, this chain rule. This is very important. But let's do this. Let's try to find the derivative of f of t. So I will simply write here f prime of t. That means the derivative of this function we want to find. So first of all, you know, we have two terms, 5, and the second term is e to the power 4t plus t to the power 7. So let's try to find the derivative. So let's differentiate the first function, the first term. So what's the derivative of 5? So the derivative of 5 is 0. Okay, plus I'm going to differentiate the second function. But then, you know, here we have e to the power 4t plus t to the power 7. This looks very strange, you know, because we don't know what's the derivative of this guy. But we know for sure that the derivative of e to the power x is, so maybe can someone tell me what is the derivative of e to the power x? It's the same thing. It's the same thing, right? So the derivative of e to the power x is e to the power x. But x can be anything, right? So x can also be 4t plus t to the power 7. So it doesn't matter. I will simply write e to the power x, but this time the x is 4t plus t to the power 7. But that's not the full story. I have to multiply by the derivative of the inside function. And so I will simply multiply this by 4, because the derivative of inside function is, if you find the derivative, this will become 4. plus 7t to the power 6. And that's it. Last question, I will do it very quickly before we move on, before we end our session. Let's say we have sine of ln x. Okay, so you see, it looks very fancy function. So, but we know it doesn't matter. The derivative of sine x is cos x, and x can be anything. In this case, x is ln x, so it's not a problem. So I will simply, if I want to find the derivative, so dy over dx equals cos ln x. Okay, so I will simply use, because we know the sine x, the derivative of sine x is cos, so I will simply use it. And for x, I will simply use ln x, but then I have to multiply, this is the chain rule, I have to multiply by the inside function. So inside function is ln x, and we know the derivative of ln x is 1 over x, and that's it. So once you know this idea, this chain rule like this way, there are also many other ways to use the chain rule, but I think this one is very straightforward. So then you should be able to differentiate all these interesting and maybe apparently complicated looking equations. Okay, I have to stop here. I'm very sorry. I apologize. I'm already 10 minutes. I continued for 10 more minutes. So let me stop here. Yeah, thank you, Elif. You got the second answer. I'm going to share this question maybe on Google Classroom. Do try. Maybe I will put even more questions. Do try them, but if you're stuck, do ask me or ask your friends and so on. This is one of the most important rules you have to learn, okay? Then the second last and the last topic, optimization and integration, maybe we will do next time, okay? So I think we have to stop here because the chain rule is very important. I really want you to understand. Any comment, any queries? Please do share with me right now. Okay, so if that is the case, let me stop here at chain rule. And even though my plan was to continue with optimization and introduction to antiderivative, but we spend more time on understanding the derivative function, and that was important. I'm really happy because you were asking questions and we were trying to find the answers. So that's how we should proceed. So let me stop here. If you have no more question, I'm going to end the session in 1 minute. And I'm still here for 5 more minutes, by the way. Once I end the session, I'm going to stop the recording. If you want to ask anything else, do let me know, or if you have any comment, so you can be with me. I'm still here 5 or 10 more minutes, okay? Thank you very much. And stop recording. Yeah, thank you.